We use graph filters and graph neural networks to learn ratings in recommendation systems. We contrast their performance with the use of linear regression and fully connected neural networks. We use the movie length 100K dataset as a benchmark. This dataset contains 10 to the 6 ratings that 943 users assigned to 1,682 movies. The ratings for each movie are between 0 and 5, from no stars to 5 stars, which your TA Juan Cerviño thinks you should find familiar. We will train and test several parameterizations. We pose the recommendation system as a learning problem in which we use the mean squared error loss restricted to the prediction of the rating of item I. The training set contains pairs XY in which we are given ratings of different users and we attempt to predict the ratings of specific items. We want an AI that produces good estimates averaged over all items and over all users that are part of the training set. We consider two parameterizations that ignore the data structure, linear regression and fully connected neural networks, as well as two parameterizations that leverage the data structure, graph filters and graph neural networks. The goal of running these 4 experiments is to compare their performances. Begin by considering linear regression. It brings down the MSE to about 2, and this is quite bad for ratings that vary from 0 to 5. The graph filter reduces the training MSE to about 1. This is not too good, but the challenge here is that humans are not that predictable. An MSE of 1 is considered good in a recommendation system. If we consider the test set, we see that the performance of linear regression is even worse, whereas the test MSE for the graph filter is about the same as the training MSE. The graph filter generalizes well from the training set to the test set. The most important observation to make here is that the graph filter outperforms linear regression. Both architectures are linear, but the graph filter leverages the underlying permutation symmetry of the rating prediction problem. When we look at the comparison of fully connected neural networks and graph neural networks, the fully connected NN reduces the training MSE to about 0.8. This looks like a great accomplishment, particularly when we compare it with the training MSE of the graph neural network, which is reduced to about 1. But the fully connected NN does not do well in the test set. The MSE reduction in the training set is illusory. The fully connected neural network does not generalize to the test set. The GNN, on the other hand, has a test MSE that is about the same as the training MSE. The GNN generalizes to the test set. The important observation to make is that the graph neural network outperforms the fully connected neural network. The GNN leverages the underlying permutation symmetry of the rating prediction problem. Our final comparison is between the graph filter and the GNN. The graph filter and the GNN both do well in the training and test set. They generalize well. The GNN does a little better, not by much, but an extra 10% performance is not irrelevant. The important point to make is that the GNN outperforms the graph filter. This is because the GNN offers a better stability versus discriminability trade-off. Our final experiment is to observe that a GNN can be trained on a graph with a small number of nodes and transferred to a graph with a larger number of nodes, maybe a much larger number of nodes, without having to retrain the filter tensor. In the case of this recommendation system, we grow the graph from 200 to 800 users and observe that there is no degradation in the MSE. In fact, the MSE is further reduced. This is a phenomenon for which we still do not have an explanation.